Are we doing this video?
Yes.
It's recording?
Yeah.
Okay, it's because it's red. I was just wondering whether it should turn green.
I think they're live.
Okay, welcome back. Today we'll be talking about wrapping up the datasets, data types section that we started last time, and then we'll talk about the visualization alpha, the marks and channels. But first, any questions about last lecture, homework, lab? Who went to the lab yesterday? Was it useful? Okay, so we'll be doing this for all of the homeworks going forward because we just think it's like a good way to repeat stuff. Cool. Anything else about the homework or anything else? Okay. So I'll do a quick recap. We talked about datasets, types, and data types. So dataset types, what can be visualized, tables, networks, fields, geometry, and data types, which are the fundamental units, which in combination make up the dataset types. We distinguish between structured and unstructured data. We talked about that visualization is really mostly concerned with visualizing structured data, and if we have unstructured data, we usually do some process first before we actually visualize it, such as NLP or computer vision like object recognition or something like that. The data types that we're talking about here are different from what you kind of think of as data types in the programming language. These are like the items, the links, the attributes, positions, and grids. So this is kind of like the structural or mathematical interpretation of the data. And so remember the different, the difference between items and attributes. Items are these individual entities that are discrete, things like a patient, a car, a stock, a city, a company, or something like that. And this is often called the independent variable, because those things, they exist independent of what we are measuring. And then the attributes are what we measure about those independent variables. So things like the patient height, patient blood pressure, the car's horsepower, the car's make. And because those depend on the independent variable, we call them dependent variables. Jump over this. We talked about other data types. Links really express relationships. Positions are really only important in spatial data, and grids are sampling strategies for continuous data. So then we reviewed the dataset types in detail. Like we have tables where we have flat tables, where one item per row, and each column is an attribute. This is kind of like the typical Excel spreadsheet that you see. You have usually, or you have to have like a key in your table very frequently that is like implicit, just a position. But it has to be unique, and like in this classical definition of the table, we do not allow duplicates. And the multidimensional table, like basically is the same thing, but I have to index based on multiple keys. So we had an example where I have to have gene expression versus patient, and I have to use both keys to get to actually one of those values. And then in like a 2D display, I can of course only encode a single attribute. Let me jump over this again. Yeah, so this is our example with the multidimensional table that I talked about, and I could stack them if I wanted to have multiple attributes. We then talked briefly about graphs. Graphs are like a set of nodes or vertices and a set of links or edges that connect these vertices. Graphs captures any kind of relationship that we can think about between items. So that like the data type here are the links, and the nodes here would be the items. And then there's special types of graphs, such as trees, where we don't have any cycles that have special properties that we can leverage in many different ways. And this is like a very common data structure, of course, as well. Fields are really about attributes, values associated with cells, and the cells, they kind of contain data from a continuous domain. And continuous domain is anything like what we observe in nature, such as temperature, pressure, wind velocity, or anything like that. And this can be commonly measured or simulated, and really, like, the tricky bit here is how do we properly sample and interpolate the data. Talked about a couple of different grid types. These are kind of like the sampling strategies, and like it goes from like very simple to like a uniform grid to very complicated and unstructured grid. Where kind of like has different pros and cons, right? The unstructured grid is the most flexible, but also the most expensive because I have to store position and connections. And then we talked about geometry. This geometry is the shape of items. We mostly use this in the context of this lecture. We mostly use this for geography, and we don't really deal too much with how we visualize geometry beyond just maps. It's not like it's usually more of a computer graphics or CAD topic. Okay, then we talked a little, or we should now start talking about attribute types. So we haven't talked about this before. If we talk about attribute types, we distinguish between, like on the highest level, between categorical and quantitative attributes. Like categorical are like just like categorical or nominal data types are where you really have classes, but you don't really have any like relationships between those classes in terms of order or something like that. So we can compare equality, like are like types of fruit or movie genres or file types or anything like that. But we can't say like JSON files are better than Adobe Illustrator files, right? This is just like a classification. We don't have any expression about order or anything like that. In the middle between categorical and quantitative is our ordinal data types, where we have something like greater and less than defined, but we can't really do math on it. So like an example would be the shirt size or rankings or car classes. Is it a compact? Is it like an SUV, or is it a truck? Right? There is a size implication in here, and so you could use like this to order that, and that would be an ordinal data type. And then finally, quantitative is where you can do any kind of math on top of it. Things are like the length of an object, the weight, counts, or temperature. So that's kind of like the three main data types that we'll be talking about, and we'll further distinguish some of this. One interesting distinction here are interval versus ratio scale. So what does 0 degree Fahrenheit mean?
It's 400 Kelvin. So.
Yeah, but why is why is it there?
Because that was 0, the lowest you get with mercury.
I don't know whether that's true.
Is it like offset from absolute 0?
I think back when they introduced the Fahrenheit scale, they had no idea about absolute 0.
It's the point at which the water that Fahrenheit was using when he created the scale froze.
That's Celsius.
And that is true. The water he was using was a saline solution, so he added salt to it. And there's theories that Fahrenheit actually had like just the coldest day he experienced, and like later on he came up with this saline solution to kind of have something a little bit more fundamental to that. But so like what I'm getting at here is 0 in Fahrenheit isn't particularly meaningful, right? We all know it's pretty cold and it's pretty unpleasant, but it doesn't really mean too much in our lives, right? 0 degrees Celsius is the temperature at which water freezes at like a certain pressure, right? Like at sea level, basically. But the point here is it's also like both of them are arbitrary in some way. They're not absolute. Like think of if I had like 3 apples here, 0 apples is like an absolute value, right? There isn't really any dispute about if I count items, then 0 is something that is clearly and well defined. And in the interval scales, I don't have like an absolute definition of 0. So there are equal difference between successive points of a scale, but the position of 0 here is arbitrary. And these scales are kind of like frequent. Like the question that you can ask, that's not like not 100% true always, but if the question is, does 0 mean nothing or none, then you definitely have a ratio scale. It's not always true. Another example for interval scale is dates, right? Like the year 2019, somebody has picked an arbitrary reference point that was of some cultural significance to some part of the population, but this is not when time started. That's something to be aware of. So, like, if you have an interval scale, you really should only compare difference, but do not calculate ratio. So it isn't meaningful to say, like, if we have a 100-degree day, the 100-degree day is twice as hot as a 50-degree day, right? That doesn't make sense. Ratio data, quantitative data types are data types where we have like the relative magnitude of scores and the differences between the matter and the position of the 0 is natural and fixed. So there's nothing there of a measured entity or observes. We can do things like length, the mass, age, weight, speed, and here I can measure, like of course, differences, but also meaningfully measure ratios and proportions. So if I like run 100 meters in 10 seconds and twice as fast as if I run them in 20 seconds. And that's something that I couldn't say about temperature. So this is kind of like a summary that like what kinds of operations are permissible or possible for these different data types. So like to recap, on nominal categorical data types, we can only check for equality. There's nothing else we can do, there's no ordering. For ordinal data types, we can check for equality, but we can check also for smaller or greater than. For interval data, we can in addition also kind of like do addition and subtractions, and for ratio data where we have like a meaningful 0 point, we can do also proportions and multiplications. That's kind of like a useful thing to think about, and when you want to express something in like a numerical scale, really keep in mind, is it an interval or a ratio scale? So, little quiz. What are 50-meter race times? Ratio, correct. You're a college major. Ordinal. That implies a value system that might not be shared between everyone. There is this like idea of purity of the field, right? I would argue that this is categorical or nominal, right? Amazon rating for a product. Ordinal? Depends, right? This is like GPA or like liquid scores on some survey, right? You can think of it, depending on your philosophy behind it, you could say it's a ratio, or you could say it's ordinal. So both are actually like...
Where's 0 defined at?
What's that?
Is 0 defined in the Amazon rating?
Well, it means absolutely terrible, but no, I would agree that 0 isn't really a super meaningful concept here. So I would go for ordinal, yeah. IQ scores.
Either ordinal or...
Ordinal, interval, why not ratio? What's a 0 and an IQ score, right?
68 standard deviations.
Yeah, but it's like, it also doesn't measure like what it's supposed to measure well, right? So like the example I always give, like if my cat were to take an IQ test, she would clearly get 0, but she's still not completely dumb. So yeah, it's like, I would argue that this is an interval scale, or maybe even an ordinal scale. Product name? Nominal category.
Sort of alphabetically.
You could sort it alphabetically, but that doesn't mean that this is meaningful, right? This is just like you can always sort something by some criteria, but it's not inherent to the data type. So one other important distinction here is sequential versus diverging data. Sequential is like homogeneous from minimum to maximum. So if I have like race times for 100-meter races, that's clearly sequential data. Diverging is when I have 2 or multiple sequences that meet. So like the classical example is an elevation data set, because sea level is something that's super important to us, we could actually create like a diverging color scale where sea level is 0, and then we have above land and below land, right? So this is a diverging color scale. Also, you could say temperature of water below or above freezing or boiling. So that here we have like a 3-segment sequential color scale, numerical scale. So here's an example of what, can you spot something in this example here? Anybody can see something? Those are in the news a lot right now. Florida, but I did use a bad color scale. I used, like the top one here, uses like a non-diverging color scale to visualize an elevation data set, right? So this clearly is not a good choice. If I like set this properly here to like 0, it's meaningful, and I have a diverging color scale, then I can clearly see like the familial land shape. So like a quite obvious example of why choosing the right color scale matters for something like this. We also have other structures in data. So for example, whenever we talk about time, we often talk about some kinds of cycles, right? For example, like if you talk about human activity, we usually have like a yearly cycle. We also have a weekly cycle, or we have like a daily cycle in some ways. So here is an example that shows respiratory disease cases on a circular layout. And so here in the left, we have a 25-day pattern. And so we see kind of like some hotspots here when people go to, this is kind of like the darker, the segment here is the more frequently did people visit a doctor's office. If we do a 25-day pattern, we kind of don't see anything really. But if we switch this to 28 days, we clearly start to see weekdays, right? So basically, people don't go to the doctors on the weekend. They go with increased frequency on Monday morning. So that's something that you can clearly distinguish, and that's very common in any kind of temporal data. So here is another larger term cyclical pattern. This is like Google Analytics data from like a course website I hosted a while ago. And so first you can see like summer is dead. Nobody really looks at the course website. But then if you looked at the larger pattern, you would see that this like summer is dead, and the semester where it's active, it's busy, then it goes down again. But you can also clearly see weekends here. So like we have like the weekday and then weekends, weekday, weekends, and so on. That was actually during the summer, and at that point somebody had made the course website the default website on lab computers, and so we see this pattern extremely strongly. Okay, so let's review like these data types. So we have, here's a table where we have like order ID, order date, order priority, product container, product base margin, shipping date. So this could be some like simple database for like a company that ships products on the internet, for example. So what I've highlighted here is our item, or our element, or our independent variable, like one example of it. Then we have the attribute or the dimension, the dependent variable. That would be, for example, product container or something like order priority. Then we have our semantics at the very top. And now a couple of questions. Where are the keys?
Orders.
Keys could be order ID. Are they the keys? No. So where are the keys? Yes, the keys in this case here are the row number. Because we have like multiple products or multiple boxes even are part of a single order. What are the attribute types that we have here? So, oops, I didn't show this. Okay, so what about order ID? Is that ordinal or interval or categorical? Yeah, you could like, if you don't know more about the system, you could say it's categorical, right? But they're probably also in sequence of something how it was ordered, so it might be ordinal. I don't think interval or ratio makes sense here. Order date? Interval. Order priority? product container. Or, yeah. Can be categorical, could also be ordinal, right? Because we have small box, large box, wrap bag, which is probably even smaller than a small box, medium box, jumbo box, and so on. Product days margin. Ratio, yeah. The ship date, we already had a date set interval. So I think that like this is like the base data model. This is the low-level description of the data. But we also can have like a conceptual model on top of this, which is kind of the mental constructions that really include semantics and supports reasoning. So for example, here I have like the data would be 1D floats, and conceptually that would be temperature. Data would be 3D vectors of floats. Conceptually, this would be space. So kind of like the meaning of the data also, of course, plays a big role. And then I can use this actually to kind of like convert, for example, from a data model where I have floats to a conceptual model of temperature to a specific data type where I have like continuous to 4 significant digits in quantitative, or I bin it into hot, warm, or cold as ordinal, or I have even like a nominal like applied to whatever toast or my cake, it would be burned versus not burned. So we can always kind of like start from a lower level, and by using like a conceptual model on top of this, derive other data types from it. And of course, in reality, like it's not gonna be so clean, right? Like you will have tables that are combined with networks, attributes to have hierarchies. Data types can be transformed as I like. So in reality, life is complicated, and we'll basically have to like make these data transformations decisions as we create the visualization to simply communicate data. Okay, that wraps up the data lecture, and I want to move on to this to the lecture about the marks and channels. And to do that, I wanted to do like a simple question. So my question to you guys is, think about how can I visually represent two numbers, for example, 4 and 8. Now, don't have a whiteboard here, so I'll try this. Okay. So, any suggestions? How can I visualize two numbers, 4 and 8?
4 apples and 8 apples.
4 apples and 8 apples. Okay. Excuse me if I don't draw apples here, but I'll just do this. Okay.
Like a bar chart.
I could do a bar chart. A pie chart. Challenging my skills here. So that would be 4. 8, the proportions are probably wrong.
You can use the numbers 4 and 8.
Yes, I can use explicit encoding.
You could use the numbers and have the text size match some type of size.
Now we're getting fancy.
A line plot.
A line plot?
So we have a dot at 4 and a dot at 8.
Use text.
I can use text.
4. And you could factor it to primes and count the number.
We could, but then, yeah, well.
Binary strings.
Fine, okay. There's a lot of different encodings now, right, that I can do with symbols. I could say, hey, let's use French words, or let's keep the graphical encodings beyond the text and the numerical one.
Darkness.
Darkness.
Oh, saturation.
Let's see. Great. Any other ideas?
Size would be dot size.
Size, yes.
Stack bar chart.
black bar chart.
You could have it animated, so 4 spins so fast.
Yes, I could do animation. I can't really draw that, but flickering, I could also do something like texture, right, if I wanted to. Nobody suggested color. What?
Oh, darkness is not.
Well, no, I'm like talking about color hue.
Square and then offset maybe.
Yes, I could do something like that.
Sides of the polygon.
Exactly.
Yeah.
I could do something like curvature.
Angle.
I could do an angle, which is kind of related to a pie chart in some way, right? So what we kind of see here is this: there is like one thing that we haven't actually mentioned, at least not explicitly. We have it somewhere in the line chart, is kind of like just saying like the height of 2 dots. So like the point here is that there's a lot of different things that I can do, right? But what is going to be easier to read? Something like this or something like this here?
Probably the bar chart.
The bar chart, like we kind of like, there is not, these are not all equal, right? Some of them are better encodings and some of them are worse encodings. And so this is really what the rest of this lecture is about. For these different data types that we just talked about earlier, what are the different possible visual encodings? So we call this either the visual variables or the marks and channels. And so, like, what do I mean by marks and channels? A mark is something that like graphically represents items or links. So, for example, if you have like 3 people, each of them would be represented as a mark. The channel change appearance based on an attribute. So you kind of see the relationship between like the independent variable and the dependent variable here. Channel change appearance based on an attribute that is defined on the item. And I call these channels either channels or visual variables. Well, both are terms that are used in the literature, so they're completely equivalent, right? If you read the Tamara Muslim book, it's called channels. If you read like papers, it's often called visual variables. So what are our marks for the items? So we have things like points or lines or areas or volume in 3D to represent an item. And so these are fairly obvious. We also have marks for links. These are containment and connection. So we kind of like talked about these when we talked about the Gestalt principles. So these are the things that identify the independent variable, right? There's like each of these points or lines or areas is an independent variable. Each of those links that are visualized by containment or connections is also an independent variable. We can also nest something like containment. Here's a technique that we'll talk a little bit more when we talk about set visualization. So the channels or the visual variables, as I mentioned before, they control the appearance proportionally to or based on attributes. And so the most common ones here are position, where we have horizontal, vertical, or combinations, shape, size, color, tilt, and volume. All of this goes back to Jacques Parisin. He's a person, a French photographer, who really formalized this vocabulary. He wrote this book, Semiology of Graphics, originally in French, but there are actually English translations. And he kind of came up with the theoretical principles for these visual encodings. And so here is his table, which is kind of similar, but not exactly the same one that we'll be using today. So he had, in English, position, size, gray value, texture, color, orientation, and shape. And he had the different marks, points, lines, and areas. And he was thinking about this in the context of cartography. So this is from the 60s. And so how can we use them? So here, like as an example, in this bar chart, my mark here is a line, right? The bar itself like the area doesn't really matter. I really only care about the height, so you can argue that this is a line. The channel that I use here is the length of the line, but also the position of the top of the line, right? Because those bars are actually start at the same point at the bottom. So we can also either look at the length of the bar or the top of the bar for position. So what we're encoding here is one quantitative attribute, and then potentially one categorical attribute, like the identity of the item. If we wanted to use a point mark, we could here use the position channel to create a scatterplot and mix two quantitative attributes about it. So here we only have like position as our visual variable or as our channel, and the items are visualized as just as the points. If we want to add an additional attribute, we could, for example, say, let's add hue to visualize a categorical attribute, or we can say, in addition to that, let's add size for an additional quantitative attribute. And so, like what we are seeing here is that we can combine those visual variables to create something, to visualize something a little bit more complex. But of course, there are limits to do this. Another way that you can approach this is to use redundant visual encoding. So here, I'm using actually 3 redundant variables in this bar chart. First, I'm using the length of the bars to encode the numerical values. Second, I'm using the position of the top of the bars to encode the numerical values. And third, I'm using the color value, the darkness, to encode the numerical values. And these redundant encodings can be quite powerful if you need to, if you really want to emphasize a point. This is a bar chart I found on Twitter about the amazing snow year we had. Anything that you can see here that's wrong?
What's the scale?
What's the scale? Do you think you could add a scale and fix it?
The log scale?
I'm not sure about the log scale. Yeah, so what you see here is that they basically have some like television graphics package, and they simply like probably use Illustrator or something like that to drag these bars up and then put numbers on them. But there's no proportionality, right? Like 17, like this bar here isn't 10 times as small as 180 inches here. So clearly, this is wrong, and you will see like a lot of those charts, and usually Fox News is a great source for these kinds of charts. So one rule, and that you should always follow, is to use the channel proportional to the data. So you should never do anything like that, where you have basically just use graphical marks and don't actually use this channel to encode the underlying data. So we distinguish between 2 types of channels: magnitude channels, where we can that we can use for ordinal and quantitative data, where we can ask questions such as how much or which rank. And the common examples are position, length, and saturation. And on the other side, we have identity channels, where it's really about categorical data, where you can ask the what questions. And here we could use shape, color, or spatial region. So this is the table from Tamara Munson's book. So you see on the left the magnitude channels, on the right the identity channels. So on the left, everything for ordered attributes, including ordinal, quantitative, including interval and ratio. On the right, the categorical attributes. And this is ranked. So you have the most efficient ranks at the top, position on a common scale, and then it goes down in perceptual efficiency. Position on an underlined scale, 1D length, tilt, area size, area or 2D size, depth or 3D position, color luminance, color saturation, curvature, and volume. And so, like, basically, what this is saying that my kind of like one of my design principles is I think about what is the most important piece of like the most important thing in the data that I want to visualize, and then I apply the top available visual variable to that. So usually, like I primarily want to encode something with position. And then for identity channels, we have spatial region. So that's what like you would do if you facet a chart, or in like if you create bar charts, you could also, like you separate them by space. You could use color hue, you could use motion or shape. People don't really use motion that much. Shape is much more common, and color hue is very common. So let's take apart this chart here. Go to the website. So what are the, take a look at this is across US company, tax rates vary greatly. So we have here S&P 500 companies and visualize how much tax they pay. So what are our marks? The circles are the marks. And what are our channels here? Maybe raise your hands so we can. Yeah. Color is a channel.
Also size.
The size and also position. Yes. So position, like, can we be a bit more specific?
Horizontal.
Exactly. Horizontal position in X is what we have here. So what does color encode? Like what kind of variable? What is the data type of that?
Quartiles?
The type of company.
I'm not sure that's true in this case.
Tax rate.
What's that?
Tax rate.
Can you say that again? Category?
Tax rate.
Tax rate, yes, but it's also binned, right? So it's kind of like a binning of the tax rate. So we have like essentially what they made here, what they did here is they converted the scale, the continuous scale into an ordinal scale of bins, and now they have like a very dark, and then a medium dark blue, and a light blue, and then a light orange and a dark orange for that. Okay, so what does the size encode? It's a little hard to see, maybe. Yes, market capitalization, so how big the company is essentially. What does the position in X encode? Yes, and in this case it does so precisely. What does the position in Y encode? Nothing, exactly. So it's just basically to make space for these elements. What's cool about this visualization is I can also, like, industries, somebody mentioned industries. Industries are categorical attributes, right? So I can actually facet this whole thing to now show the industry view on this. And so in this case now, like, how is the categorical attribute here encoded? Position, yes, by space. So we kind of like have a unique position for each of these industries. And it's quite interesting to see, like, low tax rates are something that's very common to utilities, and then high tax rates is energy sector mostly. So yeah, I think this is a quite nice visualization, and it also like comes with a pretty rich context and gives you like detailed information. Also has some metadata, including like the overall average tax rate for these companies. So this is a little bit older, from 2013. So I'm curious what this is post-tax cut. So, like, when we talk a little bit more formally about those channels, we can like think of them in a couple of different dimensions. So first, we can ask the question: is it selective? Which means, is it distinct from other marks? And can we easily make a difference between two marks if they vary, for example, only by a little? Is it associative? Does it support grouping? Is it quantitative? So that's basically the distinction between magnitude versus identity channels. Can we quantify the difference between two marks? Then order, magnitude versus identity. Can we see a change in order? And then length here means how many like unique marks can we make? And you'll see that this all varies considerably depending on the channel that we talk about. So as you saw in the table before, position is the strongest visual variable that's available, and it's also suitable for all data types. So we can use this for categorical or ratio data. It works for anything. So usually this is your first go-to thing, right? If you want to encode something, you should try to do this with position, but sometimes it's not available. So for example, if you wanted to encode data on top of a map, your position is already taken up with geolocation. So then you have to choose another visual variable. One other problem of position is that if you have a lot of items that have similar attributes, then it leads to cluttering. So let's suppose in a scatterplot, I have like a very dense region, and I have a lot of points on top of each other, so they might not be distinguishable. So it is selective, it is associative, it's quantitative, it is ordered, and we have a fairly big vocabulary. We can notice like differences in position pretty well. And so like all of these like yeses are a reason why position is good. And so here, like the canonical example for positional encoding is a scatterplot. Here we have position, like this is a chart from the New York Times comparing men's versus women's median weekly earnings. And so we have position here in X and in Y, but we also have these lines that give us some, like that have a meaning, like equal wages along the diagonal, and then women earn 10% less, so 20% less, and 30% less. So we also have position information, how much is this dot away from this line. So we have a couple of different things going on in this scatterplot here. Position really, like everything great that I'm saying about position really only holds in 2D. Here's a 3D scatterplot, and it's really hard to distinguish, like, let's suppose this orange block here at the very back. What's the value of that? It's really tricky for us to read this, right? So there's many other problems with 3D, but basically the power of position is only really applicable in 2D. And in 3D, we start there's many other problems such as occlusion and all the depth cues we need on the screen to really reveal this. Length and size are good for 1D, okay for 2D, and bad for 3D. It's pretty easy for us to spot an item that is bigger than another item. And we should also note here that if we have line bars, like here at the bottom, we're using both length and size and position redundantly, as I already mentioned before. So for example, this here is much harder to do like a judgment of, like, it's obvious which one is bigger. But if they were closer together, this would be like a harder task than if they were really aligned to each other. So for like 1D length, it is selective, it is associative, it's quantitative, it's ordered, and we have also pretty high length that we can use. So this is a reasonable encoding, and we'll talk more about like the limits of this when we talk about this perception paper. Yes.
So for 3D, what about if it's animated, like rotating a little bit? Does that include it?
So animation and like rotating and interaction is necessary for 3D. I would say that usually, like if you do something like t-SNE where you want to get like a gist of what is going on, like where things are close and clusters and so on, it's not terrible, but it's still terrible to read actual values. So if if you have some dimensionality reduction, might be an interesting solution, but if you have actual values that you want people to read, it's still not useful. Here is this example that I showed before, the bubble size. So here we encode the different, like the budget, like how big the budget for a certain discretionary spending position is, and like the 2013 budget proposal. And we can clearly see that we have like the largest bubbles. Here is this one and this one. So we kind of like get a good sense of these relationships. And I talked about this as being a tricky visualization because of red-green color blindness, right? Value, luminance, and saturation are okay for quantitative data, especially when length and size are already used, like on a map, for example. They are selective, they are associative, they are quantitative, but somewhat with problems. So we can't really, like, it's not like we have a perfect sense of, like, what are the magnitude differences between two shades of gray. There are studies that we kind of like, this breaks down, especially at the very light and very bright end, very light and very dark end of a color map. And we have a kind of a limited length, so we can usually only distinguish like 7 or 8 shades reliably, maybe even less if we have distractors or distance between them. So here's an example of a diverging value scale map. So this is like a New York Times map of the 2016 election, and I picked out Salt Lake City here. We are using a color value like on a diverging scale, like Republican versus Democratic, and you can clearly spot where the hotspots are. And you can kind of like guess, like here we have a 77% Hillary voters, and then up here we have like 69% Donald Trump voters, and so we can clearly spot that like that is like downtown is different from, let's say, the avenues and so on. So you can zoom in here more, and of course you can zoom out and then yeah.
There's another bubble in that.
Notice though that we have some counties here, for example, in this very large block here, we have 197 votes for Donald Trump, right? And so that kind of shows us a little bit of the problem of visualizing this kind of data on top of maps, because like we have a disproportional effect of like in very rural areas, and we'll talk more about this kind of stuff when we talk about maps. What's it?
Provo is green.
Provo is green, yeah, this is even the color. Yeah. So color, and by that I mean color hue, is good for qualitative data, like the identity channel. We have a limited number of classes. I talked about this when we had the color perception lecture. Like we cannot distinguish reliably more than 7 or 10 colors. And it does not work for quantitative data with lots of pitfalls that we talked about them. So if you want to use color, just be careful. And I already mentioned this before, I'm going to repeat it. A rule of thumb for me is to minimize color usage for encoding data and use it for crushing or for pop-out effects that I want to achieve. It is selective, it's associative, it's not quantitative, it's not ordered, and we have a limited length. Here is like a bad color example. This is the mean annual ratio of actual well, basically how much precipitation is lost to evaporation. And we have a very, very complicated color scale here. And so why do you think, like if I didn't show you this, could you guess what the numerical values here are? So why do you think those people did this after all? Well, maybe they wanted to really be able to make it possible for people to read precise values, right? So that would be kind of more tricky if I had a grayscale. I couldn't easily make people read precise values. But for getting a gist of where do we have a lot of evaporation happening, that's just really not a good color scale. Now here's a good color scale. I showed this in my introductory lecture. Here I'm using color only, one single color to highlight people that I especially care about. In this case, this was the active football quarterbacks back then. Shape is great to recognize many classes. It doesn't support grouping or ordering. So it is selective. It is we have limited associativeness. It's not quantitative. It's not ordered. The length is vast. So I'm showing you a picture here of different shapes, and it's easy for you to recognize each of them and to really make them they're completely separable for you. We have this huge space of symbols and logos that we all are super familiar with, but they are it's not easy to encode data with that, right? You can I encode identity, things of a category with a certain limit, but it's also not easy to if you have a logo like that, you're familiar with the logo, but if I gave you a new logo, then you would have to remember what that logo stands for in the first place. One idea that people had, related to these shapes, why don't we use, humans are really good at seeing facial expressions, right? So we can tell whether somebody is sad or not. We can tell faces apart very well. So we seem to have a perceptual system that is fine-tuned to seeing the differences in in human faces. And so people or like statisticians a statistician at Harvard, the guy called Chernoff, came up with, let's just use this human perceptual ability to recognize faces to encode many different dimensions. And so what he did is he encoded one data attribute in the distance between the eyes, one data attribute in the curvature of the mouth, one data attribute in the bulkiness of the face. And so he encoded like 7 or 8 or 9 different attributes. So what do you think? Does this work? Well, I'm saying it doesn't really work on the slide here, so it's kind of not a great question. But why does this not work?
Trying to do like ratio or interval, then shouldn't faces just be like categorical data only?
You could think of it that way, yeah. Another thought?
My big thing is if 2 of these were the same, I wouldn't be able to pick them out.
Yeah.
And these are all supposed to be the same. So.
Exactly. And you would also need very detailed legend, right? Like, what does eye distance mean? And especially, we can't use combined features, so we can't spot something that is very high in many different aspects. So here's like an interesting blog post that you can take a look at if you're interested. Because these Chernoff Faces, they have been around for a long time in the VIS community. This was like a famous statistics professor, and people really tried to push them for a while. And there's at least like 20 evaluation papers about Chernoff Faces. And so this is kind of like is a summary of this of the problems with Chernoff Faces. And like as we kind of in our exercise, we kind of saw that we have a lot of different channels. And so this here is just like a blog post that shows us 5 to 45 ways to encode 2 different numerical values, right? Like repeated icons, units, bars, line graph, percentage parse, intervals, and so on. Like there's some interesting ones in here. It's basically just exploring the design space, and many of them really don't make a ton of sense. Right? So, like I'm telling you guys that those things are different, that we are much better at recognizing position than, for example, the size of a circle. But this isn't just like, I hope you don't just believe me. I hope you question why I'm telling you this. And so people have studied that. And so one famous experiment is by Stevens, and he kind of wrote this up as Stevens' psychophysical power law. And so he charted and experimented the relationship between the physical intensity of a stimulus and the perceived sensation. So, like if we have something, let's suppose like a weight of unit 1 and a weight of unit 2, do we perceive the change to be exactly linear if we lift that weight, or do we not? And so what he did is he studied many different attributes that we can perceive in some way, things like brightness. We then tend to underestimate, we have less perceived sensation for the physical intensity of the stimulus. The same for depth and area, so we have a nonlinear underestimation. The only one where we have a linear relationship between physical intensity and perceived sensation is length. So that's why length and position are these powerful visual variables, because we kind of like have a constant impression that is exactly proportional to the physical intensity. Color saturation, we tend to overestimate, and if you ever wanted to encode data with electric shock, be aware that people tend to overestimate the force of electric shock very much.
So could you like sort of just transform your data so that it's like twice?
Yeah, so people have tried that and they've done that. So there's like perceptually optimized color scales, for example. So you can do that.
What's the variation for each of these lines?
This is kind of like a variation would be an experimental setup, right? So you I don't know now right now, but this is essentially what you get behind, like the underlying power law that's behind it. So this is the original figure. This is from Tamara Nelson's book, and this basically shows the ones that are relevant for visualization plus for fun electric shock. But Stevens actually tested many other things like heaviness or taste or loudness and smell. So like that applies for all different stimuli. So I'll run a little experiment with you guys now. How much longer is B than A? Twice. You're right. How much longer is B than A? 4 times. Notice how everybody says twice and 4 times. Like everybody is in agreement here. So and 4 times is actually correct. How much steeper is A than B?
3.
Twice? 3? About 4 times. How much larger is B than A?
3 times.
3 times, 4 times, 5 times. Notice how this how diverse the set of answers here is. So it's about 5 times larger. How much larger is B than A? 4, 8. I hear a lot of mumbling. We could now say 2 times, but we would have made a mistake. The mistake would be it's 2 times by diameter, but 4 times by area, right? So like that's a common mistake, especially for people who create infographics with Illustrator. They want to encode something in the bubble, but use diameter to encode the data. But then you get these effects where you have like what we actually perceive here is area and not the diameter of these circles. How much larger by area? 3 times. So it's really hard. How much darker is B than A? 4 times, twice. How much darker is B than A now?
3 times.
4 times, 3 times. It's about 3 times. So the point here is really like mostly to show you how good we are at judging position and length, right? And how bad we are at judging everything else. We can kind of like make relative judgments. A is bigger than B, but we have really hard time at quantifying most of these other values. And so there's like this relatedly, like there's this eyeballing game where you can like see how good you are at like doing these geometric tasks here. So adjust it to make a parallelogram or find the midpoint of the line segment. So I'll be good at bisecting this. And so I'm pretty good at bisecting a line. So I basically make a size judgment between those 2 segments here, right? But if I need to bisect an angle, I'm pretty off, right? So that seemed reasonable to me, but the green one is obviously the right one. If I need to find the midpoint here, I have to make these length judgments. Well, that was pretty good. Find the center of a circle. Also pretty good. Again, try to make a right angle. Pretty bad, right? So we're pretty bad at angles. But yeah, I have the link to this in the slides, so if you want to play with it, you're more than welcome to. So there's a couple of other factors that affect accuracy, especially like alignment, distractors, distance, and common scale. So what I mean by alignment is something like here would be an unaligned example compared to an aligned example, right? And so we are like much better at comparing these aligned ones. Distractors are like here, if I want to judge the blue, the relative size of the blue bars, it's actually fairly hard, right? Because we have, even though I just said position is such a great visual variable, the difference isn't that big, and just the 3 distractors here in the middle make this judgment much harder. So if we have them right next to each other, as I do have down here, it's a trivial thing to do. But this, again, is pretty tricky to do. And also this here is very tricky to do, right? So this all deteriorates with these kinds of other factors. One thing that is helpful if you can't align them, like bars, for example, you can frame them. And so there's studies there that you, like this works actually more, like we're much better at perceiving the differences between these framed ones. And so it's a little bit unclear why that is the case, but you can probably like have multiple things to compare, because you can compare the empty space and the full space, and you can compare the ratio, but still not as powerful as having them directly aligned. And so we, like Cleveland McGill was like a pair of researchers that did this seminal study in 1980, which kind of like is the foundation of much of perception research as it relates to visualization. And they asked participants to make these judgments, these ratio judgments or percentage difference judgments in these different conditions. So here we have a bar chart, and then we have two bars with a dot, and they ask the subjects like, how much bigger is the larger one than the smaller one in percentages? And they did this for all of these different conditions. So here we have it for stacked bar charts, or here we have it with distractors. Here we have it for stacked bar charts, but not the bottom rectangle, but at the top. So this is basically size on an unaligned scale. And then here we have them on top of each other. They also did it for pie charts. And so they found basically like what I'm talking about today is kind of like part of the foundations were made in this particular paper. And I asked you guys to read this one. This paper, that's kind of a replication study of this Cleveland McGill study. So anybody want to volunteer to summarize what this paper is about?
They replicated some previous studies that were done in a lab by using Amazon Turks, just crowdsourcing it over the internet, and found that they did pretty much the same accuracy as in the lab. Yes,
exactly. So what they were first to ask the question, can we use like basically an online recruiting methodology and an online experimental setup to do these kinds of graphical perception studies? Great. And so there's a couple of aspects to this paper, right? So what are kind of like what is their main point?
Amazon is cheap.
Amazon is cheap, yes. I would actually dispute this. It's easy to underpay people on Amazon. It's actually not cheap. Like we just ran a study and spent $4,000 in a single day, but we paid people $50 an hour. So then it's not cheap anymore. But yeah.
They're basically saying that they could use crowdsourcing for these kind of studies because the result that we got in the crowdsourcing result was close enough with your study, and they get a wider sample and it would be easier.
Yes. So we get, let's talk a little bit, I think this is great. What are kind of like the potential problems with a crowdsourced approach to these kind of studies?
I think like ecological impact you like lose control over in a crowdsourcing study.
Yeah, can you give an example?
Like maybe brightness of someone's screen, or like how distracted they are while they're doing whatever task they're having.
Exactly. People like go away and read Twitter while they do like a crowdsourced task, or they might have a really bad screen. Like we always know that projectors are much worse than like your displays. So I can't really control for all of this, which I could perfectly do in a lab study, right? We, for example, in our study that we just ran, we saw that like a lot of people browsed away from the tab that we gave them for like 45 minutes, and then continued with the task. We have unfortunately no way of measuring whether they're like paying attention when they are on the tab or they're looking at their television screen. So we kind of have like a hard time of doing precise timing information. So but this is kind of like what this means. We have a harder time setting everything up exactly as we want it. What's the benefit of that?
Pure numbers, that's really easy to just create one simple web page, send it out, and have thousands or hundreds of thousands of responses within a few days.
Exactly, scale, right? We can get a lot of people to do our task. We don't have to worry about recruitment. It would take a grad student to recruit 300 people. It would take them half a year. On a crowdsourcing platform, it takes a day. Get a comment?
In the same way that you don't get control over those environmental effects, you also don't have to worry about setting them up in the first place.
Yes, you don't have to worry about them, but even more importantly, actually, is like if I can tell you that in my laboratory setting, I have a just noticeable difference between like a shade of gray with 0.8 saturation and 0.9 saturation, that works in my lab, right? But does it work across screens of people that people actually use? So you could argue, at least for these kinds of perception studies that are meant to be on computers, we kind of get a little bit more ecological validity because we're using such a diversity of devices and of environments. So we get like, we cannot probably not find quite as like precise statistical effects, but our results that we do find are probably more applicable to this scenario on everybody's computer. Any other ideas about?
Similar vein, your audience is going to be different based on what you would get at a university, which may or may not be beneficial to you.
Yeah, so like audience at the university is usually CS graduate students, right, for the kinds of experiments we run, and that's not a very like representative sample of the general population. Crowdsourcing platforms, if you just take their like whoever they have, you might also not get a very representative population, right? But they do have like modern crowdsourcing platforms provide tools to say, hey, I only want people with a high school degree that have English as a mother tongue, for example. That's possible. So you can kind of like do these restrictions that are really hard to do in practice. Yes. Yes. So you can do it much faster. You can iterate, right? So it took them a couple of days to collect these examples. We ran 400 one-hour experiments in less than 24 hours, for example, on a crowdsourcing platform 2 weeks ago. So that's really possible to do in a lab setting. Okay, so what are the problems that you have, like additional problems you have in a crowdsourcing setup?
I didn't completely understand the ramifications of this, but they were talking about like participant overlap. Like they had to split it up into like a whole bunch of different little ones, and they were saying something I didn't fully understand about like they had like a bunch of the same people do all of them or some of them. Or things like that. They just have a lot less control over things like that if they matter. Yes,
I think it's much better with modern platforms. This is like from 2010, right? But you very often, if you have a between subjects design, so you don't want to see two people, like the same person see two different conditions, you have to be careful about that. Another problem, like if you pay people on the internet, what will they try to do? Maximize money, yeah. So kind of like game you and do it as fast as possible. So what are some strategies that they talked about in here to avoid that?
Entrance test, or yeah, like a first test that basically weeded out.
Yes. Entrance test, attention test, right? Some simple questions that everybody who pays attention gets right. They kind of like make this argument that it only makes sense to cheat by getting it completely wrong and not thinking at all about, but getting it subtly wrong and thinking a little bit about isn't really something that people do, right? Because then they have invested the time already. So what we saw, for example, when we ran our study, that we had a lot of people just click 1-1 for all of the questions we had and didn't fill in any text box. So that was kind of a way for us to screen out people that didn't really pay attention. Okay, and so in terms of the experiments, they ran 2 experiments. Somebody summarize them quickly? So the first one was the Cleveland McGill, right? And what did they change? So that's in figure 2, right? They added like a couple of conditions that weren't that popular back when Cleveland McGill did the study, like tree maps, for example, judging like this here. This wasn't a technique that was used at all when the original study was run, but they're now fairly frequently used, and these bubbles are also fairly frequently used nowadays. So they added these stimuli to them. And so what are their findings, and how consistent are they with Cleveland McGill results?
We found out that with, I think, rectangles and circles, the results were fairly similar to trees and vectors. But in case of tree maps, we found out that when they have like a squarified version of the blocks, then it's difficult for people to recognize the things.
Yes.
And they prefer a more rectangular version.
Yeah, cool. So what do you think? Would you trust these kinds of results?
They mentioned that they had to drop outliers. I'm not sure if the McGill study dropped outliers as well, but it seemed like they had to drop even after getting a lot of people in there, things that were greater than 40%. So I'd be pretty interested to see what the raw data is to make my judgment.
Yeah. So what you're hinting at is an important thing, right? If you do statistical analysis, you have to make a lot of decisions. And all of these decisions you have to articulate in some way. You have to like really say, why did I drop those people? And I don't know how they didn't do this in detail in the paper, right? But they probably have a supplementary material where they publish the data and discuss all of these little choices in detail. And so then you can go in and validate this. That's kind of just good practice nowadays. These guys also did replication work with data that somebody else published a couple of years later. So that's cool. If you publish a data set like this, somebody else can go in and kind of disagree with you with your approach, and then just use your raw data, use a different statistical approach, and then maybe dispute your results. Okay. So a more meta question: who has read these kinds of papers before? Show of hands here. Not that many. Was it accessible for most of you, or? Okay. Cool. So we'll do a couple of those in the future. I think it's just super valuable to also see where all of this really comes from. Again, I'm giving these high-level guidelines in the lecture, but most of what I'm saying and most of what Maranson writes in the book is essentially based on research papers just like this. So this is the summary of what they found. These are log errors. So they had what they essentially found. Cleveland McGill's results and their results were fairly consistent. You have interestingly a little bit more variability here in the bar chart examples. But what I think the most important takeaway here is that the ranking is consistent, right? So the ranking between Cleveland McGill and their crowdsourced results is consistent. So if we use this as design guidelines, we can actually have pretty good faith in the results here. And this is a version of this stuff that Jock McEnlaw kind of published in 1986, and he distinguished between attributes, visual variables for quantitative, ordinal, and nominal data. And you will see there's a lot of overlap with what I showed before. And this is kind of a little bit intuition-based. And people have spent a lot of time studying this and formalizing all of this since. Okay, so I kind of want to wrap up a little bit earlier today by going about just talking about the separability of attributes. Because one thing that you see if somebody starts out with visualization, if I have 5 dimensions, I'll just use an additional attribute to encode each dimension, right? So, and there's ways to do this right, and there's ways to do this wrong. So, for example, if I have a scatter plot and I want to add color to it, it's completely separable, right? I can those two don't interfere. A red mark is still, I can just as well see its position as the blue marks. If I start changing the size, then we do have some interference, right? Because the central position of the circle isn't quite as easy to spot anymore compared to the smaller ones, and we could get more overlap. So we have some interference. And also, if we vary size, color starts to change in appearance. A very small dot that is red looks very different to us than from a large dot that is the same red. So we kind of perceive this more intensely if it's a larger dot. So there is some interference if you do that. So I would, for example, not mix the size of a mark and then add an additional quantitative attribute with saturation or value. You do not want to vary width and height of these charts because we here have significant interference, right? These elements they have now pretty random like the area isn't really proportional to the data that I want to encode anymore. And what I definitely cannot do is to take the RGB values of a point and say I can encode one in the red channel, one in the blue channel, one in the green channel, because that is completely not separable, right? So here we have major interference. And so we have to be very mindful if we talk about, if we start combining them in some way, that we really still have a visualization where we can separate these attributes well. Okay, this wraps it up for today. We'll continue on Tuesday with an advanced E3 lecture, and then Thursday we'll have another theory.